Okay, folks, apologies for today. Kids' electricity ran out in school and crash, so they had to be brought home. You are going to, after this little video, be able to do the maths on page 78, page 79. You should be able to finish your exam questions at this point, so there will be some Mass Spec maths in there. And just a reminder, this Friday you're going to have your end of topic on periodic table and atomic structure. So the last day, this is where we left it. We had looked at these. I'm going to ask you please to add into your diagram. This is acceleration in an electric field. And this is separation in a magnetic field. So you're just going to add those into your diagram. So accelerate in an electric, separate in a magnetic. We had gone through our stages. So vaporization does what it says on the tin. We're turning it into a vapor. Ionization, we turn them into positively charged ions. So that was the V, the I. The A is the acceleration. And now we've just said your ions are sped up in an electric field. And the reason they do that is so that they all have the same speed. So this is obviously electric field. So that is our acceleration step. So that was the V, the I, the A, and then we do the S and the D. So the S is the separation step. And we've just drawn on our diagram that the positive ions are deflected by a magnetic field according to their masses. The lighter they are, the more they are deflected. Now this separation step blurb is also the principle of mass specs, how they work. So our positive ions are deflected by a magnetic field according to their masses, and the lighter they are, the more deflected. So as well as being stage 4, it is also the principle of mass spec. Okay, so that kind of makes sense. We made ions, we sped them up, and now we are going to separate them on the basis of their mass by deflecting them using a magnetic field. So that is the V, the I, the A, the S, so now it's left with the D. So the D is detection, and the beam of ions passing through the machine triggers a little change in an electric current and detected. So usually the questions they like to ask you are, what are the steps in sequence? And then say something about one of them, and what is the principle? So if you know the steps, you can work out the blurb that goes with them. And as we said, this one is your principle. So the basis for how a mass spec works. So your positive ions deflected in a magnetic field according to their mass. Important to know. So the next bit of this then is, I've showed you at the beginning, this is a mass spec. These are the results you get. And very clearly from this, you can tell how many isotopes are there, which isotope is the most abundant, which is the least. So how do I know how many isotopes are there? I'm literally counting the lines. So 1, 2, 3, 4, 5. There are 5 isotopes here. And then which is the most abundant isotope? It's going to be the biggest bar. So this is the most abundant. And the least abundant is the smallest bar. So this is our least. Now mass spec has a lot of uses. Similarly here, we know that 35 is the most abundant, 37 is the least. Similarly here, 70 most abundant, 74 the least. It'll just go on and on and on. Very easy to figure out. Mass specs are really important in not only determining different isotopes, but they're also used to identify unknown compounds. So forensic science will use this an awful lot in their drug testing and in crime scene analysis. In terms of the maths isn't terrible. So I'm going to go through 2 examples with you, and you can stop if you want to pause it and see can you do it yourself. So this is the piece of information that you're going to be given, and you have to link the percentage to its isotope. So we have 75% of atoms are Cl35 and 25% of them are Cl37. And when we're doing relative atomic mass, it is the average mass of an atom compared to 1/12 to the mass of an atom of carbon-12. So it's an average. So of these, this will give you the hint. Most of these atoms are Cl35. So my answer will be close to 35 when I'm done. So how do you set this up? You essentially 75 by 35. You're adding that to 25 by 37. And you're going to divide all of that by 100. And when you are done, you will have your relative atomic mass. So in this case, it worked out to be 35.5. So just to say again, you have to multiply your percentage by your mass for both and divide by 100, because 75 plus 25 is 100. So we have a look at this one. So if you want to pause now and try it, you can. Okay, so you've paused and you've tried, and when you've come back, you should know at this point, because 79% of it is magnesium-24, then your answer should be close to 24. So again, you make your link. So 75 multiplied by 24, added to 10 by 25, added to 11 by 26, and you can see your relative atomic mass in this instance is close to 24. So you have on page 78 and 79 some questions. See what you can do with them for homework. We are going to do this when I see you the next day in lesson. Before we get there, we're just going to go on to this last little bit. So this is a kind of standalone thing. We don't really do a whole lot more of it in TY, but we will use it all of the time as soon as we start back in Form 5. So you should remember from solutions, solute is the thing that gets dissolved. So something like salt. A solvent is the thing which dissolves the solute, so something like water, and a solution is both. We've had now relative atomic mass in terms of a definition, and we're now going to look at relative molecular mass. So remember, we said it's kind of working backwards, and the only word that is missing that we need to have is the word average when we write our definition. So relative molecular mass is the average mass of a molecule this time compared to 1/12 of the mass of an atom of carbon-12. Whereas relative atomic mass was average mass of an atom compared to 1/12 of the mass of an atom of carbon-12. So chemists use this an awful lot. It's their bread and butter. So 1 decimeter cubed is the same as 1 litre. So if I want to make a 1 litre solution of NaCl, I need to use the mass numbers present on the periodic table to be able to do this. So my solute is NaCl, my solvent is water, and my solution is going to be sodium chloride solution. So we use the mass numbers, and this is the way I set them up. So if I look at my periodic table, the mass number of sodium is 23. My mass number of chlorine is 35.5. I add these up together and I get 58.5. So if I was now, remember we said, oh no, we haven't said because you're not Form 5, but there's no units for relative molecular mass. But I can weigh out 55.5 grams and put that into 1,000 centimeters cubed into a litre, and I can make a solution of known concentration. Okay, so there's no units for RMM. Now, in the state exams, students lose mark if they ask you to do this calculation and you make a boo-boo and you decide it is 57.5 is what comes out of your calculator, and you just write down this as final answer and you didn't show them the working out, then you lose all of the marks. Whereas if you have it right, so you had your 23 and you had your 35.5, but you just made a boo-boo in your transcribing, then they call it a slip, and instead of giving away all of your marks, they take away 1 mark from you. So believe me when I say some is better than none, and you can make sure that you set it up this way. So you just write your elements down the side and you add them all up together and make sure you are right. So if we were in lesson, we would have done this. and we'll do this on Thursday. Happy watching.